Section 11.9, independent and dependent events. Now we're jumping to chapter 11 just because this concept is all about probability, so it fits in nicely with what we're doing. We've talked about probability of experimental and theoretical kinds. We've talked about odds and favor. And last lesson we went into the counting principle, which figures out different possibilities, so we could do probability with that as well. Now, oftentimes, you're not just going to have one event, you're going to have multiple events. Like, what's the probability that you choose a green jelly bean first, and then a blue jelly bean, and then a red jelly bean, things like that. That's more real life-like. So those fall into independent and dependent events. Independent events are just like what the word independent stands for. It's like separate, it stands on its own, nothing relies on it. So independent events are two or more events where the outcome of one does not affect the outcome of the other. So let me just write that in where the outcomes don't, and that's key. So don't affect the other events. Okay? And that would be something like, let's say you had a hat and you had everyone's name in the class put in the hat, and you want to know the probability of choosing someone, Jenny's name. So you pull one name out of the hat and then you put it back in. So when you do the second event, it's the same as it was originally. Nothing has changed. There's still, say there were 30 kids in the class to start with. Well, once you pulled one name out, you put it back in, there's still 30 kids in the class. You haven't changed anything. The two events do not affect each other. Dependent events, though, are opposite. Dependent events are two or more events where the outcomes do affect one another. Okay? And I'll just use quotation marks from there. So this is something like if you were to maybe be pulling jelly beans, and you pull one jelly bean out and you eat it. Now whenever you go to pull the next jelly bean, there aren't as many in there, so it changes things. So let's take a look at just some examples to figure out when it's independent, when it's dependent, so that we know what formula to use when we get there. Example 1, tell whether the events are independent or dependent. In letter A, you toss a coin and it shows heads. You toss the coin again and it shows tails. So our two different events going on here are tossing it once, tossing it twice. Now it's a coin, so nothing changed. Once we tossed it once, it shows heads. We mark that down on our paper. When we go to toss it again, nothing is different. It's the same coin. It still has one head, one tails. So these are independent events because the first one didn't affect the second one. They're separate. Letter B, you randomly draw a name from a hat, then without putting the first name back, you randomly draw a second name. So again, let's say you have this hat, there's 30 names in there, and you pull one out, and it says Jenny, like I said. So you pull Jenny out. Now, instead of there being 30, there's only 29. So this is an example of a dependent event because now your probability for choosing the next name is going to be different because there aren't as many possible outcomes available. Letter C, you roll a 5 on a number cube and then you roll a 6. Well, our two events are rolling a 5 and then rolling a 6. So really we rolled it twice. Nothing changed the second time. It doesn't matter if we got a 1 the first time, a 5 the first time, 2, 3, 4, or 6. The second time is a completely new roll. So these are independent events. And the last one, you randomly draw a marble from a bag, then you put it back in the bag and randomly draw another marble. Whenever you replace it, as we're saying here, that's going to be independent because you put it back in, you replaced it, you put it back into the bag. So it's just like it was originally. It's like nothing ever changed. So those are independent. Now the reason it's important to know the difference is because they both have different formulas. So the probability of independent events is just when you multiply the two events together. You multiply the two probabilities together. Okay? Or if you have more than two, you multiply all of them together. And the way it's written notation-wise, we'll say we have two events. Event A and event B. And again, you could have more, but we're just going to use two. You would write the probability of A times the probability of event B. And A is just standing for event A, B is just standing for event B. Okay? And that would be the probability of A and B happening. This is what you do, A times B. So that's all you have to know. You multiply the two probabilities together. And if we look at one involving that, example 2 says a computer randomly generates 4-digit passwords. So there's 4 digits. Each digit can be used more than once. What is the probability that the first 2 digits in your password are both 1? Okay, so each digit can be used more than once. There's 10 digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. Don't forget about 0. So we have 10 different digits that we can choose, and it says they can be used more than once. So this is independent because once one's chosen, it can be used again. It's not like it's taken out of the pool. So there's 10 possibilities for our first digit, our second digit, our third digit, and our fourth digit. If we wanted to know the total outcomes, we would just multiply all these together like the counting principle, and that would tell us. But we aren't asked that. Here we're asked what is the probability the first 2 digits in your password are both 1. So this is our first digit. What's the probability that that's a 1? Well, we have 10 options. The chance of getting a 1 is 1 out of 10. Then for our second digit, we have 10 options, 10 possible digits we can choose from. The chance of getting a 1 is 1. So we have 1/10 times 1/10. We're going to multiply the two probabilities and we get 1/100th. So the probability that your first 2 digits in your password are both 1 are 1/100th, or 0.01. Example 2 you try says, what is the probability of rolling a 5 on each of 3 different number cubes? Again, this is an independent problem because it doesn't matter what you roll the first time. It's not going to affect what you get the second time because it's a number cube. The 6 numbers are still there. So we have 3 number cubes that we're rolling. We want to see what's the probability of rolling a 5 on each of the 3 different number cubes. Well, there's 6 different numbers we could get the first number cube. Same with the second and third. Okay? Now the probability of rolling a 5 on the first one is 1 out of 6. The probability of rolling a 5 on the second one, independent, it's still 1 out of 6 because we have the same options available. And then the third one is still 1 out of 6. So we're just going to multiply. 1 times 1 times 1 is 1. 6 times 6 times 6, or 6 cubed, is 216. And if I write that as a decimal, remembering that probabilities always range between 0 and 1, it is 0.00463, on and on and on.